Okay, I think it's time to start. So, any question from last time? Yeah. So last time we're starting on these properties of Laplace transform, and as we said, that looks very similar to the Fourier transform, but now we need to consider this ROC thing. So every property here, we need to consider how they change the ROC of your Laplace transform. And so we start with a very good example, the linearity. So just like all the Fourier transform, Laplace transform also has this linearity property, but now we have this weird condition of ROC must be something that containing an interaction of the two ROC of your linear combination. And this containing means that your ROC can be bigger, because as we see this example, so although you think this doesn't happen, in some weird example it happens where you are combining two things and maybe are subtracting each other, and they have the sample at some place. Here they have the sample at -1, and when you subtract them, the pole disappear, and your ROC are bounded by poles, so your ROC extend out to this next pole at x equal to -2. Okay, but in general, your ROC should be an intersection of R1 and R2. So if you have intersection of R1 and R2, you have the root of s bigger than -1, but because this pole got cancelled, so your ROC can extend a little bit. Okay, that's the example of ROC getting bigger than what you expected. And anyway, so let's see the next property, time shifting. So we have small x, Laplace transform to big X, and we think about what happens if we do time shift. Well, time shift in time domain. So t becomes t to t minus t naught, and then just like all the Fourier transform, you get this exponential factor in your S domain or frequency domain. So you get hr e to the minus st naught here. And ROC here doesn't change. So that's very nice, because well, at any point, if it is converge or not converge, you are just multiplying a number. So the convergence doesn't really change, and the ROC doesn't move around. Okay. And so we have time shifting, and similarly we have frequency shifting, although S is not quite frequency, so it's called S shifting. Okay. So if you shift S, then similarly you will get this e to the shift S by S naught, then you get this e to the S naught t factor in time domain. But now ROC shift totally, right? Because, well, obviously you shift by S naught, so all your ROC should shift by S naught. But ROC we only really care about the real part, so shift by this real of S naught. And yeah, so ROC shift like that, but it really everything as planned should shift by S naught. So for example, if you have a pole, their imaginary value matter. So the pole will shift by S naught if you shift everything by S naught. So say you have a pole at A, then when you shift all the S to S minus S naught, then you have a new pole at this A plus S naught. Okay, and so here we have some pictures showing how this happens. Describing how this happens. So you have starting with some ROC here, and you shift everything by S, and so say S is something positive, and your ROC shift by this real of S naught. And yeah, and also, so you can also shift by S naught that's purely imaginary. So if S naught is j omega naught, then your ROC doesn't shift because the real part of S naught is 0. But the things in your plane still shift, because that's same as so you see in the time domain you are tying times this e to the j omega t. So if you are shifting by j omega naught, this is actually a frequency shift. and so it's like modulating your signal with this HY e to the j omega naught t. Okay, and obviously ROC doesn't shift as we say because this thing doesn't have a real part. But if a pulse, then your pulse will pulse of zeros, they will actually get shifted by this j omega naught. They go to this a plus j omega naught. Okay, question? So RC doesn't change, but your pulse change. Okay, then the next one we have time scaling, and well, you scale time. So you start with x of t, and then now you think about what the x of t has some Laplace transform big X, then you think about what's the x of at. So you scale time by this factor a. And it's similar to Fourier transform, and once again we skip the derivation, but you will get this 1 over absolute value of a, x of s over a. And ROC change with, I guess, kind of what you expect. But anyway, your ROC will change to a times your original ROC. Okay. Yeah. Excuse me. Yeah, so your ROC will get stretched out over squeeze and even time reversal by this A. Now remember this A is just some real value. And maybe it's easier to see picture. Okay. And so we start with something. Start with a normal ROC. And then if we are multiplying t with some a that's less than 1 but positive, then your ROC will shrink in because you times your ROC with some a. So all the boundaries shrink toward the imaginary line. And also, if your a is negative, then on top of shrinking or stretching, then you will also get a time reversal thing. So you will get left and right get flipped around. So that's what I mean by R1 equal to A times R. Okay? And yeah, so the ROC will get stretched or squeezed. So obviously if A is bigger than 1, then your new ROC will stretch out. And yeah. And the AA is negative, then you will get some time reversal, so you flip left and right. So that's what will happen. And once again, as a special case, we think about A equal to -1. Then -1, then you get this x over minus s. So you see you have time reversal, then you get this s reversal. And the ROC will flip left and right. And here you can see the time reversal, you get minus t, and the s is actually not just flip left and right because you get a minus sign, right? So all the poles and zeros will flip around 0. So it will go this point-wise symmetry. If you only think about ROC, then it shifts left and right. Okay? So here we also have the time reversal. I guess this is quite important as square it. Let's square this, and we have the time reversal here. Okay. Okay. And so we have time scaling, then we have the conjugation. So what happens if we take a complex conjugation on x? And once again, it's similar to the Fourier transform. So big X will get a complex conjugation, and so in the Fourier transform, we get a negative sign in the frequency. But here it's actually we'll get a conjugation on S. This is consistent with the Fourier transform, although you cannot quite derive from there. So I say this is consistent with the Fourier transform because if S is purely imaginary, then you get a complex conjugation that's a negative sign. Obviously, from there you don't know what the real part of S should behave. But if you do derivation carefully, you actually get this. You get conjugation on X, then you get the conjugation on big X also, and but you also need a conjugation on S, on small s, and ROC doesn't change. And as before, when we see conjugation, most of the time what we want to see is what happens if X is real. So if X is real, then big X equal to big X star of S star. Okay, so this is an interesting thing. And once again, useful form is we see that X star of big X star of S equal to big X of S star. Okay. And but now things get interesting if we think about the poles and the zeros of big X of star, big X. Okay, so if X is real, then we actually see that we have a very strong symmetry on all the poles of zeros of X, big X of S. Because if big X of S has a pole 0 as X of S0, then then it also has a pole 0 as the complex conjugation S of A star. That's because I think it's easier to see from this equation. So I think about big X of S star, right? And it was S0 star, and that equal to X of S taking complex conjugation. But so let's say if at S0 you have a pole, then big X of S0 equal to infinity, and you get complex conjugation of infinity, that's still infinity. So you see that if you are infinity at S0, then you are infinity at the complex conjugation of S0. And similarly, the complex conjugation of 0 is also 0. So if X of S is 0, then X star of S is also 0. That means X of S star equal to 0. Okay? So yeah, all the poles and zeros will have complex conjugate. It should be in complex conjugation pairs. And we have kind of seen this in the example, so you might have those kind of subconsciously, but now we prove it and static. And so let's go back to see some example we had before. So let's say we have those real signal, and we see it has they have those rational Laplace transform or system function, and the pole and zero look like this. So like for this one, is poles and zero are all on the real line, so they are complex conjugation pair of themselves. And but when you have a complex, they always form those pairs, right? So for this example, you can also derive this. I guess this is for general for all the real function, but you can kind of see this from rational function because you have a rational function and I guess that's not quite. Never mind. Yeah. So if you have a real coefficient here, then you're obviously in pairs, but that's not quite obvious here. But anyway, we have a derivation here, and we see that in this case, we also have all the zeros in complex conjugation pairs, so symmetric around real axis, and all the poles are in this complex conjugation pair, or it's just on the real line. Okay. So there's some property you should remember and take it to your heart. So that's some very nice property to remember all the time about analyzing real systems. Their poles and zeros should form those complex conjugation pairs. And when you are solving some of those property derivation questions, you will use those. If we say the system is real, then you get very strong property on their poles and zeros. Okay, the next property we have convolution. And well, just as before, you have a convolution on time domain, you have multiplication in the S domain. And now the ROC is not too tricky, so ROC is you want to be converging on big X1 and converging on big X2. So it's something containing the intersection of R1 and R2. And also we have the containing because you have cancellation. So here we have a very easy example of cancellation. So if S1 look at this, X2 look at this, and you see they are just the inverse of each other. So S1 has a pole at -2, but S2 has a 0 layer, it will cancel out. And X2 has a pole at -1, and X1 has a 0 layer, so it's equal to -1, and X1 has a 0 layer, so it's all cancel out. When you multiply together, you get 1. And 1 obviously converge everywhere, so I will see its entire plane instead of the intersection of those two. Okay, that's relatively easy. And then we have differentiation, and just like the Fourier transform, you do differentiation in time, and you get HRS. Remember, it was J omega here. And ROC once again is ROC doesn't quite change, but it's containing R because you get multiplying HRS here. So well, S is 0 at 0, so if your big X has a pole at S equal to 0, then you can cancel by this S. And the derivation just like before, you use this analysis relation equation, and you do differentiate on both sides, you get this HRS. And similarly, you have differentiation in S domain. And here we show the derivation just like before. You give this this was synthesis equation and this analysis equation. And anyway, you get use this Laplace transform equation, and you do derivation on both sides. You get this HR minus T. Okay, and ROC shouldn't change here. I guess if you are converging on somewhere, then you take a derivative, it's still converging. Okay. Okay. And now we have the differential property, then we can do the thing that we like to do. That is derive all the powers of those rational fractions. So we think about this thing in time domain. And we can find its Laplace transform. I guess the logic is kind of backward, but so what we know is we know the ROC of this e to the minus at u of t. The Laplace transform of this e to the minus at u of t, and it's this 1 over s plus a. When with ROC being bigger than minus a. Excuse me. Yeah, so this is a first example we see all the time. And now we take the DDS on this side, and you will get this HR minus T on the tan side. And you can move the, you will get a minus T on the T side, but so if you move the minus sign on the other side, then you get minus DDS 1 over s plus a equal to this thing. Yeah, it's the Laplace transform of this thing. And this thing, just as before, we can get a second order fraction. Okay? Because, well, it's a minus 1, and minus 1 equal to minus 2. Yeah. So we'll take this differentiation here, and you get 1 over s plus a squared. And RC doesn't change. So RC is still bigger than minus a. So you check out because, well, it has a second order pole at minus a, so it's either bigger or less, and it probably doesn't change size, so it's a bigger one. Okay, and so this lets you solve the Laplace transform of, the inverse Laplace transform of higher order of those partial fractions, those 1 over s plus a. And yeah, so similarly you can do this once again and get a third order, and here we have a formula for nth order. You can also try to derive it yourself. So it's the power of t times this decaying potential, and obviously divide by some constant factorial. So let's say everything again. So t to the n minus 1 divided by n minus 1 factorial times e to the minus a u of t. has Laplace transform 1 over s plus a to the nth power, and with ROC real of s bigger than minus a. Okay, so this is the equation you can use to do all the inverse Laplace transform and for inverse Laplace transform for rational function, which will happen when you solve linear linear differential equations. Okay, question. And okay, then let's see an example. Yeah, as we said, we have the higher order, and now let's see the inverse Laplace transform of the rational functions. So we have a rational function here, big X equal to 2s squared plus 5s plus 5 over s plus 1 squared times s plus 2. So it's nice we already figured out on the lower side. And then we do partial fraction expansion and skip the calculation. Hopefully it's not too hard. Here we have nice numbers, so we have 2 over s plus 1 squared and minus 1 over s plus 1 and plus 3 over s plus 2. Okay. And well, ROC doesn't change when you do partial fraction expansion. And then we need to do the inverse Laplace transform of all three parts, and as we say, we need to look at its left side or right side. And here we are getting this nice because we are on the right of everything. So because here we only derive the right side. Okay. So anyway, it's right of everything because we have a point minus 2, point minus 1, and it is bigger than minus 1. So it's right of everything, so we use the right side inverse Laplace transform. And so we read from equation, so 3, then 3 here, and the 2 go to this minus 2. And minus 1 to minus 1 and e to the minus 1. And this one we just say, so 2 here, and the square give you a t here, and 1, so you have e to the minus 1. And obviously everything times u of t. And you can kind of see here that we need to think about this ROC. And we only derive this for ROC being the right over the pole. So we have the nth order pole at the minus a. And if you are to the right of this minus a pole, then inverse Laplace transform is this. And if you think about the left of the pole, then you need to do the derivative of the other equation. On the left of pole 1 of s, 1 over s plus a. And but anyway, that will be in the table later. So that's how you do inverse Laplace transform for any rational function. We just complete that because we have the differential property, so we can derive all those 1 over s plus a to the nth power, the inverse Laplace transform. Okay. And what you do is you do partial fraction expansion as before, and you need to look at your ROC carefully. It's to the right or left of every post. Okay, and finally we not quite finally. Then next we have we had differentiation. Now we have integration, and integration we actually only do one of them, I guess. In integration in S domain is weird, but let's think about integration in tan. Okay, and integration in tan. Well. I guess it's a bit weird, but anyway. So integration in tan, you can think of it as the inverse of differentiation. So excuse me. Yeah. So inverse of differentiation, and when you do differentiation, you get s here times big X of s, and yeah. So for integration, you get 1 over s to cancel the s there. And ROC is the intersection of your original ROC, but now you get the extrapole at this 1 over s. Extrapole of this, yeah. 1 over s is the extrapole at 0, so you need to take the intersection with 0 s bigger than 0. And this we can actually do a derivation. We can do derivation from the convolution property. So because this function itself is already a convolution. It's a convolution between u of t and x of t. You can see, yeah. You can think this a little careful. If you just do a geometric interpretation of the convolution, you need to flip the u of t around, and it's something like cut over n t, etc. And anyway, so we have this convolution expression for this integral, and then if you do Laplace transform on this convolution, then we know you do Laplace transform of this, it should be the multiplication of Laplace transform on each of them. So Laplace transform of u of t, we didn't explicitly say, but we actually already seen it because it's this exponential decay thing. Right? It's this exponential decay thing with a equal to 0. So with a equal to 0, it's just one race, and and we should take the real is bigger than 0 part. And yeah, and obviously the x of t has a Laplace transform big X of s with whatever our CR. So taking them together, the Laplace transform of their convolution should be just one race times big X of s, and with this RLC. But so I say this is a little confusing because in Fourier transform this was more complicated, if you remember. So when we do Fourier transform of those integral, we get some weird delta function term, and say also you can kind of see it from the Fourier transform of u of t is 1 over j omega plus this extra pi plus delta of omega thing. So here you don't see a delta function here, but just some difference between Laplace transform and the Fourier transform that we don't go into detail. I guess a way to solve this is you see this 1 over j omega thing. So this 1 over j omega part, if you generalize to s, then that should correspond to 1 over s, because Fourier transform is when s is purely imaginary. But then you get this extra delta of omega part, but yeah, but this only happen on the real part of omega equal to 0 thing. And so for this RLC, RES bigger than 0, then you also only actually don't see this delta function part, because this delta function thing only happen when you're on imaginary line, and which technically doesn't isn't in this RLC, because RLC is real s bigger than 0. It doesn't contain real s equal to 0. Okay. So there is something weird, but this is what we think about. We believe it to be true. And you see that in Laplace transform, the convergence is better than Fourier transform. Fourier transform will allow some weird delta function. But Laplace transform, we don't have the weird delta function here. Okay. And okay, I guess any question on this tabulator? Okay. And then let's see something new. Okay. So now we have some new theorem we never had before, and they are a bit weird, but they are actually quite useful. Okay, so the initial and the final value theorem. I guess it's easier to see the picture. So the idea is that if the signal is very special, so it has a cutoff at t equal to 0, like this. So for t less than 0 is all 0. And so it starts at some value, so even yeah, so I guess it's not so continuous, so it might have a jump at t equals 0. Okay, and then you can then you keep going, and you might approach to some value at t equals infinity, and then this jump value x of 0 plus, and this infinity value x of infinity can be calculated from initial and final value theorem from its Laplace transform. And yeah, so the theorem says that if a signal kind of look like this, So it's very important. X of 0, x equal to 0 for all t less than 0. And then, and also, so you can have one discontinuity here, so you can have a jump here, but you don't have a weirder thing, so you don't have a delta function, or even worse thing, doublet thing. The singular doublet, you cannot have then here. So if you just jump here, then you can get this x of 0 plus value, so the height here, by doing the initial value theorem. So you take a big X of s times s and take s to infinity, then it becomes s of 0 plus. So magic, but this is true. And I guess, let's finish this first. And also for if you have the same condition, so x of 0 equal x equal to 0 for t less than 0, then it's infinity value, so it's infinity limit will equal to the same expression s times big X of s, but with the limit s goes to 0. Okay, so that's the final value theorem. Quite interesting, and we don't show derivation here, but the derivation should be in 1 year homework, and it's probably 9.59 or 9.53 depending on the version of your textbook. Okay. And I guess let's get a little motivation here. Although we'll see an example very first, but let's think about. So you will see that a very important thing here is your x of t needs this strong characterization. X of t equals 0 for t less than 0, and you think that's a very weird x of t. So, well, first, there are actually some x of t that satisfy this. That is, you consider the impulse response for causal system, right? So I think that's actually something we'll do. So if you are thinking about causal h of t, then the initial value theorem and the final value theorem are good thing to let you know the initial value and the final value of your h of t. Okay. And also this t equals 0, you can, if you try hard enough, you can think about you can shift it around by just doing time shifting around. And so your x of t is starting at some t0, then you can shift it around and get the initial value. And that's kind of what you expect happen in the differential equation, right? Because differential equation usually have like initial rest. So your x of t started at some t0. And speaking of differential equation, actually variant of the initial and the final value theorem will be very useful at solving differential equation with boundary condition. But that's like the end of the chapter. Yeah, that's at the end of the chapter, and they will see that it being useful. Okay. Okay. So I guess for now we just have those. So let's get a feel of the example here. Okay. So we give two motivation, but now we have like a weaker motivation. Weaker motivation is we can use those two theorems to kind of do sanity check on our calculation result of the Laplace transform. Because even though it has a limited thing, it's actually very easy to calculate if you have a rational big X of S, as we'll see here. So let's think about using it on this thing. Okay, so this is example 4.9. We have x of t equals this thing, and it has a rational big X of S, which we didn't write here. But anyway, so we had x of t equals this thing, and s times big X of S equals to this thing. So 2s cubed plus something over s cubed plus something. And so what we say this is easy to use because consider s goes to infinity, so you only need to look at the highest order s term on both the numerator and denominator. and they match each other, so it's 2s cubed over s cubed. So this limit is just 2 here. And that should match the initial value. And we see that, okay, so first let's check that our x satisfy this t less than 0 is cutoff thing, and that's true because we are always having this u of t here. Okay, so it satisfies the prereq for our initial value theorem, and then at t equals 0 is, well, this exponential equal to 1, exponential equal to 1, and the cosine equal to 1. So it's just 1 plus 1 equal to 2. So initial value is 2 as expected because it's like a 2 exponential decay. And the initial value theorem also gives you 2 here. So it's consistent. Okay. And I guess we didn't quite have here, but we can also see the final value theorem. So final value theorem, when you take x go to 0, well, x go to 0 is easy, you just get rid of this term. Okay. You take the lowest order term, so but this is 12x go to 0, but you have 20 here. So x go to 0, this is 0. Okay, so the final value should be 0 and consistent here because as t goes to infinity, you have 2 exponential decay, so they both go to 0. Okay? So I'll give you a feel of the initial and the final value theorem. And yeah, it looks very specific, but actually pretty useful everywhere. Okay, and then we have the table of properties, but we're a bit short of time, so let's not go over them together again. As we see all of them just today. And then we have Laplace transform pairs. And we see that basically we are just having all the rational fractions, right? So we have this s, 1 raised, but so we have the spirit. So basically we are starting with this 1 raised plus a. So 1 raised plus a, we have these two things with RC being on the right hand side or the left hand side. Then we have those two different exponential decay on the right hand side and the left hand side. And then with the special case of a equal to 0, we have 1 over s, then they are actually step functions. Then you can do derivative and take those two higher powers, then you have the step function times this t to the some power, t to the minus 1. And also you take a derivative of those two things. And so we derive this. So if you're on the right hand side, then you have this right hand side exponential function times power of t. And on the left hand side, you can also do a derivative. Then you have similar thing. So it's exponential decay on the left hand side times power of t. So that's all those fractions. And I believe you can. Oh, okay. Then we have something extra, and we have the delta function Laplace transform to e to the minus s of t, and excuse me. And we have something extra, those sine and cosine. Sine and cosine, they can probably be derived by the linear combination of exponentials, etc. Okay. And then finally we have more of those rationals, and so this we just wait. Oh, okay. Yeah. Okay. Yeah. Then finally we have those s to the nth power. So if you have the hr, so you take a rational function. If the numerator is, as we say, if the numerator has more degree than the denominator, then you get those remainder terms, and they actually inverse Laplace transform to very singular thing. Then you get those singularity function u of n, and but if you think about the negative of those, that's also true. So if 1 raised to n, then you have u of minus n. Remember u of minus n is actually something converging, and this thing should be same as this thing, right? Because on the S domain is the same thing, and so this u of minus n is just this power of t times u of t. Okay, and yeah, I don't think we cover the sine and the cosine here. Wait, oh, yeah. So sine and cosine should be okay. Sorry. So sine and cosine you can just write them back to the complex exponential and use those 1 raised plus a etc. to derive them. Okay. But here you can see they have some nice form, and I guess. I guess we can say a little thing here, so you can see that this is sine and cosine are real, and you can see the poles here forms the complex conjugation pair. So the poles are the plus minus j omega naught, and that's also kind of what you expect. Sine and cosine function two complex exponential and frequency plus minus omega naught. Okay, question about the Laplace transform pairs. If not, then let's start using the properties. So we go to the analysis and the characterization of the TI system, use the Laplace transform. So first key concept is the system function or transient function. Which we already use the name of system function. It's just this big H of S. So yeah, big H of S is called system function or transient function. In chapter 4, we had you have Fourier transform, and this was big H of j omega. But now we have a general S, can be anything complex, and we think about this big H of S. Yes. So the system function. Well, the system function tells us a lot of property of the system. So, for example, we'll analyze what the H of S will look like for stable system and what the H of S will look like for causal system, etc. And then we'll also use this to solve linear differential equation of LTI system. And anyway, we start with this, and derivation we cannot skip. So derivation just comes from the convolution property. So remember, y of t equal to h of t convolute with x of t. Then you take Laplace transform everything, then you arrive at this with some ROC. Okay. And anyway, so we say we want to talk about stability and the causality. So here are the stability and the causality. Okay. They are a bit complicated, more complicated than what we had in chapter 2, where we talked then about HOT. But anyway, stability of, if you want to look at the stability of your LTI system from big H, and is if only if the ROC contain the j omega axis, so something like this, or right. Remember your ROC are strips, and if that strip contain the j omega axis, then we think this is if only if the system is stable, and the derivation is actually not quite rigorous. So the the idea is that the system is stable if only if h of t being absolutely integrable, as we say in chapter 2, and then we have not very rigorous derivation says that h of t being absolutely integrable if only if the Fourier transform is converged, and then if only if the ROC containing this line. But as we comment before, this is a bit weird because this is one of the this h being absolutely integrable is one of the Dirichlet condition. But Dirichlet condition you have 3 of them, and also Dirichlet condition is not a if only if thing. But anyway, but that's still what we believe. I guess we don't look at the weird case so much, and we believe that if RC contains the geometric axis, then your Fourier transform is very likely to converging, and that means the h of t is absolutely integrable, and and your system is stable. Okay, so that's what you will use for solving a problem RC containing geometric axis, if only if LTI system is stable. Okay, so the derivation is a little tricky, is a little tricky, but hopefully we can see the idea here. So we think big H being L3 integrable, being the Fourier transform converging, and being Fourier transform converging here means RC contained here. Okay. The Fourier transform converging and RC containing here is something that we claim to be true when we talk about the property of RC. Okay. But anyway, so that's the BLT and the causality. And causality now we really don't have this if only if. Okay. So now we have a very detailed different case analysis here. So we have that if the system is causal, then the ROC is right-sided. Okay. So I'm jumping, sorry. So if the system is causal, then obviously the h of t is right-sided because we have h of t is 0 for t less than 0. That's what we had in chapter 2. So if the system is causal, then h of t is 0 when t less than 0. So h of t is right-sided. And if you remember the property of RC we talked about, that means that so our small h is right-sided, so big H should also be right-sided. Okay. And here we just have a different name for right-sided. Right-sided means it includes the right half plane. Anyway, it should extend to right infinity. Okay. But very important here is that the converse is not true. Okay. So for causality, if you are causal, then your RC is right-sided. But if your RC is right-sided, we will see in a counterexample that it might still not be causal. But if we add more condition, if your system we know it's a rational system function, then right-sided if only if it's causal. Okay, so that's very nice. And question? I guess then let's see an example of this causality first. So so let's see a good example first where we have a rational function, and so we have a causal system, and so h of t is our favorite exponential decay, right-sided exponential decay. Okay, so it's rational and it's causal because it's 0 on all the t less than 0 part. And when we do Laplace transform, then it's our most familiar Laplace transform. It goes to 1 raised plus 1. And we'll take the right-sided ROC, so the ROC is right-sided. Okay? So if we check out here, it's rational, and you have a right-sided function, so you have a causal function, and you have a right-sided ROC. And then let's see a counterexample where we have a right-sided ROC but not causal function. And actually it's easier to see this backward. So we have our function is the same function, same exponential decay function, but we just pull it to the left a little bit, right? So if h of t is e to the minus t plus 1 u of t minus 1, so it is the exponential decay starting from minus 1. And then this thing, then this thing is not causal because you have this between minus 1 and the 0 part, where your h is non-zero. And then you do Laplace transform, and you find out that it's this e to the s over s plus 1 with with the RC being right-sided. So the RC is the same because, so I believe this is you can believe this is just you applying the time shifting property on this function. So you apply the time shifting property, you get the same Laplace transform, same RC with just h e to the s. So you see the RC is right-sided, but now your system is not causal anymore. Although your system is not causal, your system is right-sided. Yeah, and but you see that you get this h e to the s. So this is not rational, so it also doesn't break the thing we said. Okay, so we go over time a little bit. So let's start again in 10 minutes. 这里是说 x 等于零，然后这个对 t 等于零，在 t 小于零，在 t 小于零一个地方 x 要等于零嘛，那我就说，那有时候可能你考虑的 x over t 是没有真的写在 t 等于零，那个写在某个 t 等于 t 那个地方，那你可以想象说你做一些 transcript，然后可以把它换成这个形式，那你就还是可以用这东西的。对。
就是这个 n，它具体到底是？
因为它就是随便什么数字啊，就是一个数字这样。因为热旋方程可以有一个数字，因为我在猜这一堆 root， 但是可能前面还可以再多乘一个数字啊。
就是这样。OK， 对，
就这样。 Okay, let's get back. And once again, let's review the two property we have. Stability and causality, and how to interpret determinant in terms of this big H of S. So for stability, it's a bit easier. So the system is stable if and only if your ROC of H of S include your J omega axis. And for causality, it's a bit more complicated. So for original function, then the causality is easy. It says if ROC is if your ROC is to the right hand side, then your system is if only if your system is causal. And so we don't have the derivation here, but you can kind of see the derivation easily just from we can do the inverse Laplace transform the rational system, right? Because you can kind of see here. So when we do inverse Laplace transform, you break your rational system into those partial fractions, and you see that if you pick everything to the right hand side, then everything will have a u of t. So your system will be causal. Okay. And but if you are not rational, then you don't have easy characterization. So if your system is not rational, then this causality characterization is one way. So if you are causal, then your ROC is right hand sided. But as we see, your ROC is right hand sided, your system might still not be causal because you can behave right hand sided H of t like this, but it's not causal. Okay. And then let's see next example. And this is the example where we see that by specifying the property of your system, we can determine its ROC. So let's think about the system H of S equal to the system function H of S equal to S minus 1 over S plus 1 times S minus 2. So obviously it has a 0 at 1 and 2 poles at plus 2 and minus 1. And you can have 3 possible ROC. So because it has 2 poles at minus 1 and 2. And so there are 3 possible ROC, so to the right hand side and the middle part and to the left hand side. Okay. And so we see that if we give it 3 different properties, then we'll pick all the different ROC. So for example, if we think it is causal, then this is rational. So it's causal if only if, actually even if it's not rational, that's true, right? So if it's causal, then ROC must to the right hand side. So we know that if it's causal, then ROC must be this. And yeah. And then correspondingly, then we can get inverse Laplace transform of this. And we skip all the calculation, but remember if you do inverse Laplace transform, you need to do partial fraction expansion of these two things. And if you get a minus 1 pole and a minus 2 pole, a minus 1 pole and plus 2 pole. So this minus 1 and plus 2 here. And then because everything is right hand side, so you get this u of t. And that fits our expectation because you have this u of t, so this is causal. Okay. And the next one. For this thing, then you see that it doesn't equal the geometric axis. So even though it's causal, it's not stable. Okay, not stable, and you can see that it's unstable because you get this e to the 2t terms, right? So you get the exponential ingrowing term here. So this h of t is not going to be absolutely integrable. You have this e to the 2t term, it just goes to infinity. When it goes to infinity, and it's unstable. And so obviously the next one will ask what if you want to be stable. So if you want to be stable, then you also need to include the geometric axis. Then it's this thing. You need to pick the middle part, and then you write out everything. Then yeah, then you pick a middle part, and then you see it's to the right of this -1 and to the left of this +2, and then your h of t look at this. Your t is this e to the -t times u of t, and e to the 2t times your -t, and adding them together, linear combination of them together. So this will be stable, but obviously this is not causal because you have this u of -t part. And finally, then there is this one, so you have the RC on the left hand side, and this happen if you want your system to be anti-causal. So we didn't define this before, but you can probably guess. So anti-causal, it just means that you want your h of t equals 0 whenever t bigger than 0. Okay, and when that happens, you will pick the RC on the left hand side, and that will be the length of both of your poles, so you get this u of -t on both of your terms. Okay. Okay, question on this example where you have a system function and you write down its poles and zeros. And the zeros doesn't matter here, so you look at the poles here, and then you can determine your RC by specifying a property. So if you want to be stable, then you must include the j omega axis, and if you want to be causal, then you need to pick the rightmost side. And okay, so from this example, residential question you can think about is, what if I wanted my system to be both causal and stable? And okay, so if you want to be causal, then you need to pick the rightmost RC. And if you want to be stable, this rightmost RC needs to include your j omega axis. So that means that your rightmost pole here must be left of your j omega axis. Okay. So here we just by doing logical derivation, we find out that if our causal rational system is also stable. Let's see. Do we need rational here? I think. But anyway, okay, let's think about that later. But anyway, so your rational system, if you want it to be causal and stable, then all the poles must be to the left of your j omega axis. You must have a negative real part because you want to pick the rightmost RC, and the rightmost RC also need to include your j omega axis. Okay. Any question? So this is also a nice property to know. And then okay. Then let's consider something we discussed before. So this is second order system. Second order system. We didn't have a differential equation here, but anyway, the second order system has this impulse response and this system function. So impulse response and of e to the c1t minus e to the c2t, and the system function basically has a pole in the c1 and the c2. Okay, and c1 and c2 has those two values. Okay, and yeah. Now we consider. Okay, so we consider our second order system being causal because second order system is also usually a physical system. Say our second order. Wait, we don't have here. Okay, say our second order system might be like a RLC circuit, and if you are building an RLC circuit, obviously that should be causal. Anyway, so we consider it being causal, and it has poles at C1 and C2. And an interesting thing we can analyze here is that if we want this thing to be also stable, then the C1 and the C2 must have the negative real part, right? So if the real part is positive, then just as what we say here, then your RC is going to be the right of your. Oh, maybe I should just use this picture. So if you have the real part being positive, then your RC will to be the right of your geometric axis, and your system will be unstable. Okay. And when will that happen? When will that happen is, so omega should also always be positive. So omega is positive, then if your this, I believe eta, if your eta is negative, then this will be positive, right? So negative times negative become positive. So if eta is negative, then your C1 and C0 will have this positive real part, and your causal system will be unstable. So that's bad. And so that's why we didn't consider it. So if you remember from last time, we analyzed this eta to have two regions, so between 0 and 1 and 1 to infinity. But and we didn't consider eta to be less than 0. That's because for eta less than 0, you will have those real and C1 and C2, and the system will be unstable. And you can also see that from your h of t. So your h of t is this e to the c1t minus e to the c2t. And yeah, and if your c1 and c2 have the positive real part, then this thing will have some exponential growth with t. So you will have two oscillating exponential growing part, and that looks very unstable for your h of t. Although okay, that saying is a bit tricky. But anyway, if it's exponential growing part, then you want to check is this absolutely integrable, and that's not absolutely integrable because integration of the growing exponential function is infinite. Yeah, so that's unstable. Okay. Yeah, so that shows you that this causal and stable characterization by the ROC of system function is quite useful. Okay, and let's see, we should be okay today. Okay, so the next one, we go to the favorite part of every Fourier transform chapter. That's solving LTI, solving linear constant coefficient differential equations. Okay, and it's actually very complicated here because we are going to do this twice. But we don't have time today probably, so we will save the other part to next Tuesday. Hopefully we don't have Kirikan. And anyway, so for now we will talk about using this bilateral Laplace transform to solve our differential equation. And it will be very like what we do in chapter 4. So we'll write so we had it here already. So we will look at your differential equation and we write our h of s. And we do this, it's a little confusing. So we do this with the initial value being 0, basically. So basically we are doing this for, most of the time we'll do this for initial race condition. And remember, initial race condition will give you causality, and then you kind of see why we talk about all the causality here, because then you will see the being causal, and you can pick the ROC for this thing. Because this thing doesn't tell you the ROC, just give you some h of s, and it's going to be rational. It has a whole bunch of zero in the poles, and so basically you need to pick a ROC by some property. Maybe you want a stable function, or you want a causal. You want a stable system, or you want the causal system, and that will tell you which ROC you should pick from this. And but there is something else very weird, kind of weird. At the end of the chapter, we will talk about another kind of Laplace transform called the unilateral Laplace transform, and that can also solve differential equation, and is a different kind. It's not with initial rest anymore. We'll have a non-zero, some arbitrary non-zero initial boundary conditions, boundary values, and but it's tricky here because since you are not with initial rest anymore, the system you are doing is actually not a LTI system. But nonetheless, we will be able to solve those differential equations with boundary condition by the unilateral Laplace transform. But that's for next week. For now, let's focus on our bilateral Laplace transform or just Laplace transform. And as we said, we can use it to solve linear differential equation. And so those equations here. Let's run through once again. So our linear constant coefficient differential equation usually like this. So a linear combination of differentiation of y to some k's power, k from 0 to n, and also differentiation of x here. Then you take a Laplace transform on both sides, and this differentiation give you some power of s. And so here you have a polynomial of s, and on the x side you will get another polynomial of s. Then you have big H should equal to big Y divided by big X. So you move things around, then you see that it should be this X part polynomial divided by this Y part polynomial. Okay, so this thing we have done many times in midterm and in chapter 4, etc. And so you can write this big H of S very easily. But just as we say, yeah. So in chapter 4, we kind of assume it's a stable causal system, although we didn't say. So chapter 4 we say it's initial rest, so we are assuming it's causal, but actually you are also implicitly assuming it's stable, so you actually have inverse Fourier transform, right? Because inverse Fourier transform is Laplace transform on geometric axis. So we didn't say that, but whenever we have a quadrant in chapter 4, we need to tune the number carefully so that the system is stable. But now we know better. We know the Laplace transform, and we are not looking at the geometric axis only. We are looking at the whole S-plane. And so we can solve this for kind of maybe a little weirder system, but so we just need to, so we will look at all the poles here, and you know there are many possible ROC, and you just need to pick the right ROC with the information that the quadrant tells you somewhere. Okay, so yeah, as we said, you will get this H of S, and you will have many possible ROC, and you can pick the ROC if the quadrant told you something like if this H of S is stable or is causal. And just like we just do here, right? So like you have this H of S and it says causal, then you should pick this ROC, and it's stable, you should pick this ROC, etc. Yeah. And for example, so if we want to do like in chapter 4, we want the initial rest, then the ROC should be you want initial rest, then it should be causal, then you should pick the rightmost ROC. Okay, so let's see example very first. So differential equation dy dt plus 3y equal to x. And then you can just look at this and write down H of S. So you have this 1 here, so 1 over then S. So 1 times S plus 3. Okay, so H of S, look at this. And it's a very simple rational function. It has a pole obviously at -3. And so ROC can be to the right side of this -3 or to the left side of this -3. And its inverse Laplace transform is those two functions that we know very well. Okay, so it's either this exponential decay to the right side or the exponential decay to the left side. And but from just here, then we cannot really determine the H of t. But say if we know it's integral rates, so the system is causal, then we'll pick the right side, and our h of t, then yeah. So if we know it's causal, then ROC we should pick the right side. Then our h of t is this familiar thing that we know in the Fourier transform. Okay. Question. And also you see that this is a good system, is stable. Okay. And yeah. Okay. And next one. It's a more physical example, and as we say, RLC circuit, then it should become a second order equation and second order differential equation. And here we skip all the derivation, and anyway, if you have RLC circuit, then the differential equation should look like this. And here x of t is the driving voltage here, and you have LC times the dy dt squared. Y is, I think, the voltage across your capacitor here. So LC times dy dt squared plus RC times dy dt plus y. So anyway, it's a second order equation. And as before, you can read the big H of S from here. Then it should be, okay, you have it should be 1 over this LC times square plus RC times square plus 1, but we want the S squared to have nothing here, so we divide everything by LC, so you get this. Okay. And yeah, this thing has two poles because you are dividing two things here, so it's actually constant divided by second order equation, and it has two poles down here. And then you can think about where are the poles here, and let's see, and so maybe let's solve here. Let's do middle school math here. So middle school math says that if you have a squared plus by, sorry, wrong. Middle school math says that you have a squared plus bx plus c equal to 0. Then the roots are x equal to 1 over 2 minus b plus minus square root b squared minus 4ac. Okay, hopefully people still remember this. And so why are we writing here? So we want to write here because we want to look at the real part of this thing. Real part is this minus 2 minus b over 2. Okay. Oh, sorry, I write it wrong. Fail my middle school. Okay, b. Okay, yeah, minus 2a. But anyway, yeah, so minus b over 2a. And so if you look at this thing, and so that's the real part. Real part is minus b over 2a. And if you look at the minus b over 2a, is r over l over 2 times the minus sign. So if your component all have the real positive properties, okay, so if you have usual capacitor, etc., so those components should all have a real value RLC. So these RL are all positive real. So this minus b over 2a should be negative real. So you know your oh, okay. So but there might be something extra, but it's annoying. Okay, but that's when you have complex pole. Sorry. But anyway, and if you try harder, so let's skip the try harder part. So if it's try harder, then you will see that even when this part is let's see. Okay, okay, let's try a little harder here. Okay, because I already wrote down this. Okay, so let's see. Okay, so if b squared is less than minus 4ac, then this is complex. So you know your x has negative real part. And also, if so, can this be positive? The most positive thing, if b squared minus 4ac is bigger than 0, then the upper side you have minus b plus square b squared minus 4ac. But if your ac are both positive and real, then you are subtracting a real part. So then this is less than 0 if ac bigger than 0. Okay? Because you are subtracting something, so this is square root, so this is less than square root b, which is also equal to b. Okay. And anyway, what we want to say is if the things are all positive real here, then all of your roots have a negative real part. Okay, that's what I want to say here. So all your roots have negative real part. And let's finally back to our system function analysis. That says that when you take the causal ROC, you will also include the geometric axis, and that means your system is stable. So our ROC circuits are stable. Very nice. Okay. Question? Yeah. So actually this is similar to the second order equation we had before. So let's draw a little of the two possible roots. Right? So two possible roots are either both are real but are still negative, like this, or they have complex and they are complex conjugations, like this. But as we said, we take the causal ROC, so it's to the right hand side. But they all have a negative real part, so they all include the geometric axis. Okay, so ROC is like this. Okay, so that's what we want to say. Okay. So ROC circuits are stable. That's nice. Okay, and then let's go to the more example part here. So the textbook actually have many examples here, but I only take one. So I think we should have more of those questions in homework. And yeah, you can also look at the textbook example. And anyway, so now we can use those system system properties to do those detective questions on our LTI, on our system function. So for example, let's see this one. We have the following information on our LTI system. So system is causal, and the system function is rational, and it has two poles, one at -2 and one at +4. And then we have this behavior property says that if input is 1, then the output is 0. So this is constant function 1, input is a constant function 1, then output is a constant function 0. And also the value of impulse response, so h of t at 0 plus is 4. Okay, so we have those 4 properties, and ask you to determine our system function h of s. Okay. Yeah, h of s, and also always is yeah, determine the system function. Okay. So system function we need to determine is algebraic form, and we need to decide its ROC. Okay. And okay, so the system function. So we start with the first one, the system causal. So we know the ROC, we need to pick the rightmost side. And the second one I told you a lot. So it's rational, so it's a polynomial divided by a little polynomial. And they say the only 2 poles, so you already know the denominator. So the denominator should be just this s plus 2 times s minus 4 because there's those two poles. And the numerator is something, so we say it's a polynomial of s. Okay. So the second equation told you a lot, and combined with this thing and the first one, it says so we already know it's poles. Wait, do we have the picture? Okay. I guess it's not quite important. So we know we are picking the ROC to the rightmost of this s equal to 4. And although it doesn't ask, but we also know the system is unstable because your ROC will not include the geometric axis because it's bigger than 4. Okay. And okay, so the system function look like this, and we need to decide p of s, and then we need to use those two properties. And now the third property you want to use is tricky. It's tricky because what do you mean by x of t equal to 1? But so you need to notice that x of t equal to 1 is actually a very special function. This actually told you one of the eigenvalue equation because x of t equal to 1 and 1 is e to the 0 times t. Okay. So 1, this constant function 1 is actually a complex exponential. Yeah, remember we say e to the st are the eigenfunction of every LTI system. And yeah, so this 1 is a form of e to the st with s equal to 0. Okay. So if you put 1 equal into your LTI function, you should get some number times 1. And the number should be h of s with s equal to 0. So that just be h of 0. Okay. So we see that h of 0 times your 1 equal to, well, that should equal to h of 0, and you see that h of 0 is 0 here. And so we see h of 0 is 0. Okay. But you can also look at this thing here. So we have equation for h of s. So you put s equal to 0 here, then you get p of s over minus a equal to 0. And that means p of 0 should equal to 0. Okay. So yeah, so that's the most tricky part of this question, where you see this x of t equal to 1, then you realize that actually e to the st, and with s equal to 0. And from there, you see that p of 0 equals 0. And but then you remember p of s is polynomial, so it's like a power of s. It's a polynomial of s, and polynomial, if you put is equal to 0, if polynomial is 0 equal to 0, that means it has no constant term, right? So it can be like a squared plus s plus 0. It can have no constant term, so every term has at least a power of s, so you can write it as s times another polynomial. Okay. Or you can look at it this other way as the root of s, so you can factor out s here. Okay, that's easier to say. Yeah. So from there we see p of s is s times another polynomial q of s. And finally, from property 4, you see this 0 plus thing. Okay, you see the 0 plus thing, and you immediately feel that we should use initial value theorem. And indeed, we can use initial value theorem. And we didn't say, but we should check that we can actually use the initial value theorem. So why can we use the initial value theorem? Because the system is causal. Okay, so yeah. Remember when we want to use the initial value theorem, we need the x of t. So the h of t should be equal to 0 for t less than 0, and satisfied because that's exactly what the system being causal saying. So I should mark here. And causal. Okay, so because causal we can use initial value theorem. And so initial value theorem says that, so now we just write down the form. So limit s go to infinity, s times this system function h of s, it should become 4. And if you write s times h of s is now p is sq, so times s as s squared q, and over this s squared minus 2s minus 4 minus 8. Okay. Here we have the initial value theorem. And from here you basically see the result. So we have a long analysis here. So analysis says, well, you basically look at the highest order here. S goes to infinity, you look at highest order here and highest order here. And it's already s squared here, so this q of s cannot have any power of s, because if you have more power of s, then this thing should go to infinity, but it's only 4 here. So this q of s is only a constant, and what a constant be, that constant should be this 4 here. Okay. So yeah, so that's the result. Your h of s is 4s over yeah. So your q is 4, and so p is s times 4. So your h is 4s over s plus 2 times s minus 4, and yeah. And we're actually missing something here, right? Because we say we want to determine the system function. And I guess it's a little confusing, because sometimes when we say system function, we are not so clear that we want the ROC. But it's better to include ROC here. So we also have ROC being ES bigger than 4. Because it's causal, you need to pick the right side. Okay, and okay, we have about 10 minutes. It's a little weird. So actually for the next 2 parts, so even though we are shorter on time, we are a little shorter on our class schedule, but we are ahead on time for today's schedule. But anyway, so here we have the 2 sections where we actually skip, because it's well, so first we have this Butterworth filter, and it's mostly on things about chapter 6, which you already skipped. So just also skip here, but yeah. So we'll skip those, but I guess it's already in the slides, so you can read those if you like. It's quite interesting. So it says that in chapter 6 we have this kind of filter that's something like the opportune ideal Laplace filter, and you can analyze its pole structure and find out that if you want it to be really causal stable, yeah, if you want the causal stable, then you can pick its poles and 0 at the correct place. And then you see that what the system function should look like, etc., etc. That's quite interesting, but we'll skip that and let's go in superface. And I guess we can look at the open system a little bit. And then also open system, so we'll talk about this a little before, where we have example of open system that just 1 pole and 1 0 on the real line, and we see that you can have more general open system. As we said, if you just have all punctual pole and 0 pair, they are all symmetric around the imaginary line. So we'll look at this, and you will be an open system. Okay. Magnitude is constant. And here we say irrational. Oh, okay. I'm just confusing myself. Yeah. So it should be like all those point zeros symmetric around the imaginary line. And if you write the then in numbers, then it's AK and minus AK star, etc. So that's opaque system. And then you can think about if it's real, then you have even more symmetry because the real thing you have all the zero and poles should be mirrored around the real axis also. So you kind of look at this, you have up-down symmetry and left-right symmetry, and system is also called monopace if it's stable and causal and all the zeros on the left hand. And it's good because you take inverse, it's also causal and stable. Because the inverse will solve the poles and zeros. Okay. Oh, it's final zero. Yeah. And anyway, that's that. So we skip ahead quite a bit. And special factorization is analysis that looks very like a Butterworth filter. So let's also skip that. And let's go to the next part that we would like to skip. That's the block diagram representation, I think. Although this is quite useful, but you can probably learn this in more electrical engineering class. But we'll talk a little bit about it. So it's basically we want to write all the block diagram in terms of H of S. And well, in terms of big H, the block diagram, remember we are interconnecting them with parallel and serial. And in terms of Laplace transform, it has nice numbers because say it's parallel thing. Well, parallel, the output should be a summation of those two. And if you if you are thinking about system function, then because of the linearity of Laplace transform, you still have the sum of those H. And but what's interesting is you have the serial connection of your block diagram. So if you have a serial connection, then because small h you get a convolution, then you think about big H, it should be multiplication of each other. Kind of see these together. And from here, then we can kind of solve for effective system function if you have a feedback loop. So this is interesting. So let's say you have the system X put in, and you have this big weird feedback loop where you go through a system with big H1, then on the output you branch back and go through a system with big H2 and subtract to your input. So you have this weird feedback loop. Then you can solve if you have H1 and H2 here, then what's the effective LTI system here? And so we can solve this with equations. And we say this part, let's call it E, and this part call it Z. Then the Y output here, so all these things should be Y. Y should be E times H1, right? Because in the S domain, they multiply together. So Y, big Y should be big H1 times E. And then from this subtraction here, you see big E should be big X minus big Z, just from this subtraction here. And also from this system application here, you see big Z should be big H2, so this system times Y here, because everything here is Y, this branching is copying. Okay, so then you have three equations here, then you can substitute out E and substitute out Z. And in the end, we want to get equation between just Y and X. So we can see this very easy. So Y is H1 times E. Then you substitute out E with X minus Z. Then Z is H2 times Y. So Y is this function of X and Y. And finally, we want to find the effective h, thus the ratio between y and x. So that should be big Y divided by big X, and you should be able to move things around here, and you see that it's H1 over 1 plus H1 times H2. Okay, and we have 5 minutes, so we're gonna see an example. So yeah, so let's see, H1 is this 1 over S, and it's an integrator, and H2 is just minus 3, so it's like a constant system. And let's see, okay, yeah, then you see your H of S is 1 minus H1, so 1 over S over 1 plus this H1 times H2, so wait, where do I get the negative sign? Oh, because the negative sign is, we don't have a negative sign here. So it's the equivalent, so the negative 3 is my subtraction of plus 3. Okay. So 3 over S, so 1 over S plus 3. Okay. And yeah, so that's the effective H of S here. And we can also do the reverse thing we do in, I believe, in chapter 2. So we can also invert this back to a differential equation, right? Because we know a differential equation given this to a very simple one will just be this 1 give you x, and this plus 3 is just dy dt plus 3y. Okay? So we, from this feedback loop, go back to a differential equation like this. And then the next few parts, I think we will skip or have more thing about. There are ways that write your differential equation that give you rational system function, and how to write them in all forms of block diagram. There are, say you have a second order differential equation give you this direct form block diagram, and there are more forms of the block diagram, but let's skip this for now. Yeah. And okay, so although we skip a lot, we would like to end early today, and next Tuesday we'll go on, finish chapter 9 with this unilateral Laplace transform, and tell you how to solve differential equation with initial values or boundary values. And I think maybe, let's see, we might also start chapter 10, but I'm not very sure. But yeah. So anyway, that's today. Any question? Or let's see you on next Tuesday, hopefully. Okay.